All right, so a lot of times what we'll find in physics is that if things work one way, they work the other way. So we saw this kind of non-intuitive result in the last chapter that electromagnetic waves, which often appeared as continuous properties of a wave, can look like little bullets and can actually be quantized into little chunks of electromagnetic radiation. And so we've also seen the analog of that with atoms making up matter, where the atoms are like a little chunk of the matter. So there's a similar kind of relationship. And so we might wonder then, well, if electromagnetic waves have particle properties, then do particles of matter have wave properties? And the answer is, yeah, they do. And that is really critical to our understanding of the universe, is to realize that particles of matter can be thought of as being superpositions of waves. And so that's kind of interesting, but also really weird. Okay, and so let's just think about that for a second. This guy, de Broglie, was just a struggling, I think it's pronounced de Broglie, by the way, but it looks like de Broglie to me, but I think it's de Broglie. It's French. He was just a struggling PhD student, and he wondered, well, if photons have zero rest mass, but have a momentum p that's equal to h over lambda, and this is a connection between the particle and wave-like properties of photons, then could matter have a wavelength? So the idea here then is that these photons are particles, and if they have a wavelength that's related to the momentum by h over lambda, could matter also have a wavelength? So the idea then, and he used more mathematical rigor to justify this assumption, but basically this is the connection he was trying to make. So in other words, could mass times velocity for a particle equal h over lambda? And if that were true, then how could you prove it? Okay, well, one way of trying to prove it is to bounce some particles of matter off of different faces of a crystal. Okay, so if we have a crystal here that's got a certain crystalline structure, and these are layers of the crystal. This is a lower layer of the crystal. This is the upper layer of the crystal. Then we should be able to take photons and bounce the photons off of the different layers, and for certain angles you should be able to get a constructive interference of the photons, right? Because if this distance here, d, and for our purposes let's set d equal to 5.3 times 10 to the minus 10 meters, okay, now typically the size of an atom is about maybe an angstrom or two, and so that's 10 to the minus 10 meters. An angstrom equals 10 to the minus 10 meters. So this is a few angstroms separation distance, or something like a half of a picometer, or a picometer is 1/1 billionth of a meter. So these are typical crystal separation distances. Then, if the waves have a wavelength that's short enough, you should be able to get constructive interference, provided that if this distance here is d, and this angle here is theta, then the angle that we go through, the vertical, is going to be theta as it comes in. And then as it comes down, let me just draw this without all of the waves and stuff. So one comes in like that, bounces up. Another one comes in like this, and then bounces up. So how much extra distance has this bottom wave moved? Okay, well, it's gone to here. They both traveled the same distance to here. But then this distance here is d, and this angle here is theta. Okay, so that means that this distance here is d sine theta. So we have an extra distance d sine theta on the way down. Then because this angle is also theta and this is d, by symmetry we have d sine theta coming back out again. And so the extra distance traveled, delta, for the lower photon would be equal to 2d sine theta, and that would have to equal m lambda for constructive interference. This would be our condition for constructive interference. If these were photons. So we would expect then that if this condition were satisfied, then we would get a brighter beam coming out. So this would be the condition for constructive interference, but delta equals 2d sine theta equals m plus 1/2 lambda would be the condition for destructive interference. So in other words, the photons would cancel. So if this condition holds, then you don't see a reflected beam because the photon here would be 180 degrees out of phase of the photon here by the time that it left the substance. Okay, but if it was exactly an integer multiple of the original wavelength, then the wave that's traveled the lesser distance and the wave that's traveled the greater distance would line up and would constructively interfere with each other to produce a stronger beam. So this is already known, and this is something that you learned in Physics 2AB. But what de Broglie wondered is, if matter has a wavelength, could you do the same thing for matter? Could you say that if the particle is coming in at a certain speed, it would have a certain wavelength. If that wavelength satisfied this condition, then you should get a stronger beam reflected back out. And if it didn't satisfy that condition, then you should get no beam coming out. In other words, the beam of particles coming in would interfere with itself, essentially. And so this is where it gets really weird, because these beams have to be in phase for this thing to happen. So what we're really saying here, and we're saying this for the photon, although it may not have been clear to you in 2AB that the photons had to have the same phase. But obviously they do. The one that bounces off of this surface and the one that has to go off of that surface must have originally been in phase with each other. How is that possible if they're different photons? Well, it's not going to be possible if they're different photons. They're the same photon. So the photon then is actually taking two different paths. It's bouncing off of this layer and off of that layer, and then it's constructively interfering with itself. So it's in two places at the same time and interfering with itself on the way back out again. So that's what you've already done. It's an implicit assumption that the phase differences have to be the same in order for you to get a relationship like this to work. Otherwise, the phases are just going to be arbitrary. And so the same thing will be true here. The particle doesn't just bounce off of this surface or that surface, but it does both. And it interferes with itself to either produce constructive or destructive interference. And so this is where, I mean, we said before that relativity is kind of strange. Time is not the same. You've got relative realities, all of this stuff. But this is just as weird, or some people think even stranger, that the particles can be in more than one place at the same time and can interfere with themselves. And yet, this is easily measurable for photons. Is it measurable for matter? Well, let's do this for a theoretical calculation in which we have a helium atom and that's going to have a mass that's equal to 4 times the mass of a proton, roughly. That's 4 times 1.67 times 10 to the minus 27 kilograms. And let's say that that helium atom has been accelerated to a velocity of 1.635 times 10 to the 3 meters per second. Okay, so we get a beam of helium atoms moving with this characteristic speed, and each of the helium atoms has this mass. Okay? And so these are basically alpha particles. Okay? Now, alpha particles have their electrons torn off, so you don't have to worry about the fact that the electrons are circling around one of these alpha particles. But alpha particles are a type of radiation that we're going to talk about later that can go through and interact with matter and can cause radiation damage. Okay, so with these ideas in mind, then, we can solve. And let's just say that this is the initial beam that we have that's coming in to this interface between these two crystalline layers. Right, so this gives us lambda then would be equal to h over mv. So that would be 6.63 times 10 to the minus 34, again, joule seconds for h, divided by m. M is going to be the mass of the alpha particle, 4 times 1.67 times 10 to the minus 27 kilograms, times v, 1.635 times 10 to the 3 meters per second. Okay, and so punching out those numbers, what we get is that the wavelength that we would expect from the de Broglie hypothesis would be equal to save a little time. I've already got these numbers punched out here. Be 0.609 times 10 to the minus 10 meters. So this is the expected wavelength using the de Broglie hypothesis. So the question then is, can we take a beam of helium atoms and adjust the angle just right so that we get constructive interference for that wavelength? Okay, and so what's observed then when we do this, we actually take that beam that we know is traveling that fast, and we hit that that set of surfaces with it, what is observed is that we get constructive interference. The first constructive interference is at theta equals 25 degrees. So, but things are looking encouraging because we're getting a weaker beam until theta equals 25. For theta less than 25, and also for theta greater than 25, we get a weaker beam of helium atoms. And so that's just like a weaker beam of photons moving out because of partial destructive interference. So in other words, this is the condition that we're measuring for the constructive interference, and this is the first interference maximum, which is when m equals 1. We know the distance. This has been measured, 5.3 times 10 to the minus 10 meters. And so we can plug that into our condition for constructive interference here. This gives us 1 times lambda equals 2 times d, 5.3 times 10 to the minus 10 meters times the sine of 25. What we get for lambda then is equal to 0.60 times 10 to the minus 10 meters. So we compare that to this value that we got by using the de Broglie hypothesis, and we find that to a very high degree of accuracy, those two results agree. And so that means that experiment is backing up the de Broglie hypothesis that this is in fact the correct wavelength for a particle of matter, like a helium atom. Does it have to be a helium atom? No, it could be an electron, it could be a proton. But for this particular experiment, it was helium atoms that were used. And so this is not only evidence that the matter has wave-like properties, but it's also evidence for the fact that the particle trajectory is, it's got a multiple particle trajectory. It's doing more than one thing and then interfering with itself. So this is all very strange, but it's working out. It looks like this is giving us the right answer for matter having wave-like properties. And so de Broglie then made this hypothesis, came up with this whole idea, and that he wasn't an advanced established scientist yet. De Broglie was just a struggling PhD student. And in order to get a PhD, you have to do not only original work, but it has to be correct, right? It can't be wrong. But it was so advanced idea for the time that his advisors didn't know what to do with it. They didn't know whether this was legitimate or not. And so they called Einstein in. And they were really excited that Einstein was coming to their university. And so he comes in, and he doesn't want anything to do with any of the scientists. He just says, where's the manuscript? And then he disappears into this room for like 8 hours. And they're wondering, well, what's that guy doing in there? 8 hours he's looking at that thing. And finally he comes out 8 hours later, and they go, well, Professor Einstein, should we give him the PhD? And he said, well, I don't know what the requirements are for a PhD at your university, but I'll tell you one thing, he'll win the Nobel Prize for what he's done. And he did. He won the Nobel Prize for this idea of particles having wave-like properties. So it was a very courageous thing to do for your PhD thesis, basically taking on the whole scientific establishment and revamping our whole concept of what a particle of matter is.